We all love abstractions, we as developers. The powerful idea that we can hide very complex behaviors behind simple facades which allow us to talk about very complex things with a very simple language, it's what drives us in our everyday work, so we use them a lot. Whenever you come with a complicated business problem or a technical one, the answer is usually just put another abstraction layer on top of it. But today, I would like to talk not about the abstractions and the higher level principles, but instead dive deeper into the code which actually makes our applications performant, robust, and it actually runs them. Today, I would like to get back to the basics and talk about threads in Java Virtual Machine. But before that, a few notes. So if you would like to ask any questions, you can do so using the Slido. So you probably know it by now. This is room 9, hashtag GeeCON 2019. And my name is Adam Dubiel, and I work at Allegro, which is a biggest Polish e-commerce platform. And I am a team leader of teams which are responsible for building kind of an abstractions for other developers on top of our infrastructure. And one of those things are a set of libraries which we use in all our microservices. It's all based on Spring Boot. So in my everyday work, people come to me and we talk about performance problems, or we talk about, Spring and things that can happen there. And based on those experiences, I decided to create a talk which actually tackles the problem of what Java thread actually is and how can we manage them so we don't do any harm to our applications and that they can actually scale well. So let's start with the beginning. And at the beginning, it's like a big bang. So whenever you start a Java application, like a Java process, a lot of things start happening really, really fast. And one of those things, or for anything to happen, you first have to have a thread to run it in. So one of those things are creation of multiple threads. After a few, actually seconds or even less, everything settles. So the big bang is over, and now everything is stable. And you have this fixed amount of threads, and maybe every now and then a single or two threads pop somewhere, but usually it's like a set landscape. So let's look at it with the numbers from a different perspective. So I made a graph, and to do this, I took a sample project from Spring Boot starter page. It's just a simple Java application with Undertow HTTP server. And what I did is I added logging to graph what threads are created at what time, whenever this application starts. And you can see that it's like 25 seconds there. Actually, it's only 10 seconds before after this long break between 10 and 25 second mark is time I waited before I started flowing the traffic. So if you look at it from the different perspective, how many of those threads are there, not only when they appear, looks like this. So basically, after we start the app, we have something like 35 to 40 threads. And then, after the traffic starts flowing, and this is the big uptake, we end up with something like 115 threads. Is it a lot? And what do they actually do? So the first threads, well, whenever we start something, well, this is when the different virtual machine threads come to life, and we're going to dive deeper into this section later on. Then the Spring context boots up, and it brings with itself another 15 threads or so. And then once the traffic starts flowing, the majority of threads is created, meaning 80 or so. So let's talk about this big bang moment, meaning the moment when the process is born. Everything I'm going to talk about during this talk is based on Linux systems. So most of us have our production systems on Linux, so let's just stay with this. And in Linux, we have something called the process tree. So there is this very special process. It has a PID, process ID, of number 1. And in modern Ubuntu systems, it would be systemd. and it's responsible. This is the root of the whole tree, and it's responsible for spawning other processes. And this is an excerpt from ps3 command, which shows a system in which I SSH'd onto and run a bash shell. So we have the bash shell as a leaf of the system. If I run Java version in this bash shell, well, Java process is just gonna come up as a leaf, as a child of bash shell. Well, of course, usually we don't run processes on production just by SSHing and running it in the terminal. There's something else like supervisor or systemd taking care of our process to run. So you might see something like this. But what the process actually is, I've said this word like 30 or 40 times already during this talk. So let's focus on this, what it is. A very simple abstraction to understand the processes is that it's actually like a collection of threads. So a thread is something that runs your code. And all the threads which can access the same memory are a process. They create a process together. And each thread with its own stack trace and everything, but also with an access to shared memory. So you cannot share memory between processes, or at least not natively easily so, but you can share the memory between different threads. And as I'm going to show you later on, this border between a thread and a process is very, very thin one in Linux systems. So let's talk about threads. So I show you this command, the output of this command, it's ps3. And if I was still running the Java process and run this ps3 command, you could see something like this. So you can see there's another level, one more level, showing up next to the Java process. There's something funny about those things, because you can see that the name of the process or this thing is actually in curly braces, and not just simply a name. Why is it so? And what are those entities shown? And you can also see that the numbers or the process IDs or some kind of IDs are actually, they're pretty similar. So we have the Java process 1876, and we also have those, things next to it, and the naming space is actually really, really close. So you have 1893, for example. Well, what if I told you that those are the threads of virtual machine, and actually we can see them in the system Linux tools because JVM thread is a system thread. So whenever Java wants to spawn a new thread, there's no magic happening inside my virtual machine. What it does is it goes to the system library and asks it to spawn a thread. And just to prove it, this is a piece of code taken from OpenJDK, the exact place in which all the threads are created in Java. And we are using here the pthread library, Linux library. And so, what does it mean for us, for simple developers? Since JVM threads are system threads, we can use Linux tools to observe them, and also they are scheduled using Linux scheduler. So the system takes care of everything around those threads. So if we just took simplest system tools, we could see them. We could see our Java threads. So first of all, in /prots, you can see under the process ID, you can see the tasks being threads, and you can see all the IDs of all the threads that we spawned in Java. Well, of course, we're not using those kinds of things all the time. So we might use PS or we might use top to see them. But anyway, you can see with the -h flag both the process and all of the threads that it created. So let's get back to this PS command and talk about some definitions. There are two identifiers here. There is a PID and TID. PID, it's a process ID and you probably already know it. But there is also the other one, TID, being thread ID. And this is the ID of the thread, not the process. The funny thing is, that although they are treated separately, they actually share the same namespace. So as you've seen, the numbers were actually growing, like the process and the thread IDs were growing in the same namespace. So they share the same namespace. And so when could this knowledge be actually useful for us? Well, imagine this situation. So there's a host and, something's eating up our CPU time. So, it's Friday, it's 9 p.m. and we're at the party and we're on duty and we have to do something about it. So how to quickly determine which process, or better, which threads are eating up our memory? So let's take this one. This is like PS command output. I've shown you the PS command that I've shown you before. And we can see the column which shows the CPU usage. So we can see the CPU usage per thread. So we already know that there are 4 threads there which act up, which do something funny. Well, if only we knew which threads are they. Well, I have their IDs, I have the thread ID of each one of them, but how can I connect this with what Java knows? Because, well, those are just numbers. In Java, I have names. So the problem is, how can I match system thread and JVM thread? Well, in Java world, when you want to learn about threads, we usually use JStack command. Or actually, well, maybe you shouldn't use JStack, you should use JCMD instead. Okay, so we have the thread dump, and for each thread, you have this one special line. I'm going to zoom in for the important bits. So what we have is a name. Great, because the name is what we would like to know. We would like to know which thread is eating up our CPU. What's more, we have those 2 identifiers. One of them is TID. I guess we already learned about TID before. And NID. Okay, so why would I show you 2 identifiers? Well, because nothing is as easy as it seems. So this TID is actually useless for us. Okay, it shows it has the same name, but it's useless because this is just a pthreads ID. It has nothing to do with system thread ID. So what we are looking for is an identifier hidden under NID, which is native thread ID. And well, it would be too easy if it was just system thread ID. Instead, you have to use its hexadecimal form of the same number. So those are the 2 important bits in Java stack trace. We have thread ID, we have thread name and we have NID. NID being the hex of thread ID. So let's walk it step by step. So once again, I want to know what is the name of this one thread with 8521. It eats up 30% of my CPU time. Well, what I do is I change this number into the hex and then I just grab the JStack. I can do it with this kind of a one-liner. It actually works. And when I do this, what I'm going to get is the thread name. And, well, it's garbage collector, as usually in Java. So it's the garbage collector which is eating up all my memory. So, or CPU, sorry. So as you've seen, it's possible, but it's a bit mundane. So it would be great if it was a bit easier. And if you're looking for a reason to actually, upgrade your Java from 8 to 11, or even further, if you're feeling lucky, well, there is another good reason. Because in Java 8, there is this command, there is this piece of code in C++ which says set native thread name. And you know what it says? You've probably seen it a lot in your code. Not implemented yet. It's not there yet. Well, it hasn't been there yet for 20 years. But since Java 9, things changed. So they implemented this method. And what this method does is that whenever you call thread.setName, this name is going to be propagated back to the operating system. So actually not whole name, just first 15 characters, but it's something and it helps. So if you run PS3 in Java 11, this is what you're going to see. So you're going to see some thread names without actually using Java tools. It's all going to be there in system tools. And getting back to the example, you can see the GC thread, plain and simple, in plain sight, in your top or PS command. Of course, the trick I've shown you is still useful, since you probably might have longer thread names than just 15 characters, but it's a very good start. Okay, so I just know it's here. Okay, so let's get back to the application. I've shown you that there's like 120 different threads there. But is it a lot? Should we be concerned about the number of threads in our application? Let's talk about cost of a thread. And there are two categories of threads. There are implicit costs, as always, and explicit costs. So the basic ones are, first of all, the amount of memory we need to allocate for the thread for it to work, the stack memory, and it's 1 megabyte. But then we have those hidden costs, which are not so obvious. That's why I call them implicit, like context switching, like safe pointing, like actually threads being GC roots. And I would like to talk about the first two of them today. So let's talk about thread stacks, about what's actually in there and how much space do we need to allocate for it. As you may know, in Java we have those two like main areas of memory. So we have the heap memory, and we have everything out of the heap. Well, just call it off heap. So the heap is the kingdom of garbage collector. Anything that we create in Java application, or most of it, unless we're very specific about not doing it, every simple objects land on the heap. But the off heap is the place where thread stacks live. So all the thread stacks actually end up there. And to show you how much space do we need to allocate for all those threads that are created, we can use tools like native memory tracking in JVM. So this is a tool which reports on every memory allocation that whenever we go to our operating system, it gets reported in this output of this command. So I'm just going to print Java version and ask it to print how much memory it needed to do this. And there is this one section in the output which says how many threads and how much memory did I allocate for those threads. So actually, just to print Java version, I needed to create 18 threads. This number changes slightly depending, but more or less stays the same. So the number of threads. And for those threads, 18 threads, I needed to allocate 18,000 kilobytes of memory. Okay, so very complicated math. 18 kilobytes times 18 equals 1 megabyte. So each thread costs me 1 megabyte of memory. So I just checked it. It's not just I said it. This is what the tooling says. So if I needed to somehow calculate the total memory my app needs, I would have to, of course, go with the heap size, meaning like mx or xmx, and then also add up some other variables like the space that is needed for the thread stacks, meaning thread count times stack size. We already know that the stack size is 1 megabyte. Okay? And this is actually a very, very important thing to do. Like when we used to run our stuff in VMs, there was always some spare space. So we always knew that, if we get a virtual machine, we would probably ask for a bit more memory because, of the operating system, etc., etc. But now, once a lot of us are running our applications on production on Docker or any other containers, well, the things get interesting because we usually don't account for all the memory that is needed, and the Docker is actually like an executioner. So whenever you allocate even 1 megabyte above your limit, like if you said, I wanted 2 gigabytes, and you allocate 2 gigabytes and 1 megabyte, your app is going to get killed. So with operating systems, we always calculated a bit more. The system was a bit lax with all those rules, but Docker, it never forgives. So this one is very, very important. Well, so let's talk about how many threads can I create. So I have all this RAM. It's like 2 gigabytes of RAM. And of course, there is this space for the system, so I already told about it. And of course, with this heap space, so, and the off heap, like, Java's gonna do something in those spaces. So let's say we have like 500 or 512 megabytes, just to, round it up. And then we have this like 300 megabytes for some system stuff. So it leaves us with 1.2 gigabytes of memory, well, for different things, and for example, thread stacks. And so if I wanted to ask you how many threads can I create for this system, well, it's simple, actually. It's like 1.2 gigabytes times 1 megabyte, and it gives me a nice round number. I can create 1,200 threads on this system. Not more, because, well, there's no much space for this. Well, let's try it. So I have this kind of box on my computer. It's a virtual machine. It has 2 gigabytes of memory. Oh, you can see it here. Okay. So, and I have this piece of code which all it does is create new threads all and over again. So I'm going to run it. It's called thread spawner. What just happened? So I just told you that using these techniques, using, just spawning the threads, we should be able to create like 1.2 thousand of them. And instead, I created something like 5,000. How can it be real? Well, actually, it's not real. So you can't use the memory if it's not real. And the trick is, well, the operating system is actually pretty intelligent, and it's pretty smart. So we have those two kinds of memories available to us, and you probably might have stumbled upon it in the top output. So we have this thing called virtual size, virtual memory. And this is not a real memory. It's just a address space the process can access and can use, but it doesn't mean that it's actually available in the physical memory. So whenever you go to the system and just ask for some space, it can say, well, just go ahead. You have the address space here. Just use it. But it's going to be virtual unless you're actually going to use it. And if you would like to know how much memory your application uses for real, well, you have to look at the other metric, which is called res. It stands for resident set size. So this is the total memory your application is actually using. And it's like the only metric which can tell you with 100% certainty how much memory do you need for your application. And you can see it in system tools. So if I go back to my virtual machine and I once again run this program, it's going to run in the background, and I run top on the other thing here, you can see that my Java application has like you could see for a moment that it used something like 6 gigabytes of virtual memory while using something like 9 megabytes or 90 megabytes of real memory. So that's the trick. So unless you're going to do something with those threads, unless they're going to allocate things on their stack, unless they're going to traverse the frames, well, you're not going to use this memory. So the system is not going to stop you from spawning as much as you want, up to the point. So there's one thing that's going to stop us, and it's called limits, system limits. And there is one of those limits which is called max user processes. And you might wonder, the limit is called processes. Yet each thread that you're going to create actually adds up to this limit. And once again, this border between thread and the process is very, very thin. So they actually, add up to the same limits in operating system. So on this system that I've shown you, I can spawn something like 7,800 threads or processes, whichever comes first. Okay. So the other cost of a thread is context switching. And lately, for some years now, there's been this movement in Java world to switch into things like Webflux or Netty servers. And actually, why do we want to do this? Like, all these non-blocking things. Well, at the beginning, I shown you that the app that I created was using 120 threads to serve traffic. Well, how many CPU cores do I have usually at my command? Well, on this kind of machine that I spawned, it's only 4 CPUs. So I have 4 CPUs, and yet I've created 120 threads. This means that what they must be doing for most of the time is waiting, because I can only run as much as 4 of them at each given moment. So what they do is they run a bit, switch, run a bit, switch, run a bit, switch, and so on and so on. So the thing with Webflux and Netty, all this non-blocking thing, is that instead of making a bunch of threads wait, why not utilize this resource better and just have smaller amount of threads which actually do things, and delegate the waiting to the operating system. So let's dive deeper into context switches. So what is a context switch? I already told you that we just switch and switch and switch. Is it for free, or does it cost us something? Well, in modern CPUs, you can graph a single core architecture looking something like this. It's a very, very high-level abstraction of a CPU core. So we have this core, and we have few caches, 3 levels of cache. You have L1, L2, and L3 cache. Why do we have 3 of them? Well, first 2 of them are exclusive to the core, so only this CPU can actually make use of them. And the third level, L3, is shared among the region. So in our case, we can say that it's simply shared between different cores. We have 3 of them because the further away you get from the CPU, the more time it needs to retrieve the data. But then, the closer you are, the higher the cost of manufacturing, and actually you have less space to put things. So the L1 is a really small one, it's like in kilobytes, L2 is like hundreds of kilobytes, L3 is like megabytes of data that can be kept in this cache. And you can see it in access times. So this is like the optimistic version, so you get the cache hit. And for L1 cache, it's like 1 nanoseconds or even less, like 1 instruction. For L2, it's like 4 nanoseconds. Then you get 1 order of magnitude more. And just to go to the RAM, it's like 100 of nanoseconds, and it's 2 orders of magnitude compared to L1 cache. And in your usual app, what you would like to see is kind of this data flowing from RAM through the caches to your CPU. So the data that is used really heavily, you might want to see it, somewhere L2, L1 cache. So this is called the working set, and you would like to have it close to your processor. And there are things in the CPUs which actually, fetch the data which you might want to use beforehand. It's called prefetcher. But what comes when all those things are disturbed by a context switch? So there was a thread running, and then another thread, or even worse, a thread from the other process comes in. So this is the other thread. This one is yellow compared to the blue one. What happens now? Well, what happens is that this data that has been stored in cache, that the CPU has been fetching, well, it's probably useless. You're probably working on the other context, on the other working set. And, well, that's a problem. Why? Because fetching data from RAM is actually pretty expensive, as you've seen. So there's been a studies about context switches, and the one that I found tells that it can, in the worst scenarios, it can lead to even 30 milliseconds it can take up to 30 milliseconds. And if you'd like to observe how much time does your application spend, context switching, you can use tools like perf or vmstat. So since our threads in Java are actually system threads, we'll also see things in tools like this. And this is why we're trying to go towards this kind of situation, when we have only few threads, which utilize CPU heavily, which don't switch so often, and all the waiting is done on the system level. So we delegate the waiting, and we only want to know when do we have to wake up and do something with the data. So let's get back to this application. This is not a fancy application. This is the old school application, like, with the blocking server. So we have all those threads, and I promised you that we're going to dive deeper into what happens in each of the stages. So this start, it's 20 threads which come to life. Well, let's take a look. What would you say is the first few threads that actually are created in Java? Well, in Java, it's all about creating garbage, so somebody has to collect it. So the first threads which come to life are garbage collector threads. And then we have VM thread and C1 and C2 threads, C1 and C2 compiler threads. So, since we're producing a lot of garbage and our code starts running, we need to optimize it. So they are also created. And then, once again, Spring Boot and traffic starts flowing. So let's talk about managing threads on our application level. So we're getting back from the system back to the application. And, you can do two things basically. You can just create threads, use new thread, create thread every time you need to do something. Or you can use thread pools. And as an example, I'm going to use this executors.fixed thread pool. So usually, we don't want to throw away threads. They're perfectly good ones, to reuse. We don't want to throw them away. What we want to do instead is use different kind of thread pools. So what happens when you trust your tools a lot? And this is an example from Spring. So you probably seen a thing called, this annotation called @async. So if you want to run something in different thread pool, you just put @async in your Spring application on top of a method, and magic happens. Well, let's take a look behind the curtain what kind of magic happens. So unless you've been really explicit about thread pool you want to run this async code on, this is what's going to be used. It's called Simple Task Executor. And I just told you that threads are perfectly good to be reused. And actually, spawning a thread costs something. You have to go to the system. It has to be created. Well, what happens here is that every time you have an async method which does not explicitly tell you what thread pool to use, Spring is going to fire a new thread for each task and then throw it away. We don't want to use it. We want to reuse our threads to remember about this whole thing. So it's easy to use, but just remember about this. Okay, so thread pools. What's the fuss about all the thread pools? You've probably seen this structure, and it's really easy. We have a array, a place for threads to be created. And, well, this is the place where thread lives. So it has an finite capacity. In this example, it's 6 threads. So we can run 6 things concurrently in this thread pool. But what happens when the pool is full? So, every thread in this thread pool is busy doing something or waiting. Well, the other part of the structure is a queue in front of it. So there's a queue in front of a thread pool where we queue the tasks which wait for the execution. And depending on the thread pool, this queue might have a different size. But let's concentrate on this fixed thread pool because this is the one which is used mostly. So in a fixed thread pool, how would you say, how big can this queue be? Well, actually, in the default implementation, it's infinite. So, it's constrained by the memory, which means that it can overflow, and it also means that it can kill your application quite easily if you have too little threads to operate on your tasks. So if the tasks keep on flowing in, it's never going to stop. It's never going to tell you enough. It's just going to keep on growing and growing and growing. And there should be something we could do about this, and there is. But we have to get out from this beautiful world of simple factory methods in executors, and we have to use the constructor for thread pool in JVM. So this is the thread pool executor, and this is the class which is used by all thread pools in standard library in JDK. And it has a bunch of arguments. So it's a bit scary. Like there's a lot of them, and you might not know which ones to use. So the first 4 of them, they actually they speak about the size of a thread pool, and if you're going to set the core pool size and max pool size to the same number, like 6, both of them, you don't have to worry about keep alive time and keep alive time unit. So this is just the size of the thread pool. And then we have the task queue. And this here you can say the implementation of the queue in front of the thread pool should be this. And usually you would like it to be some kind of a constrained array. Like array blocking queue works great. Just set the size, and whenever it gets overflown, well, this small thing is going to be called the rejection policy. So this is actually just a simple functional interface which tells, which is fired whenever the queue is full. So once the queue is full, it's going to get fired. And what can happen on rejection when the queue is full? So there are a bunch of implementations already in JDK which we can use. So just to focus our attention, this is the happy path. So we have a thread which is called the caller thread in this example, and it wants to run something in this thread pool and run free. So if there is a space in the queue in the thread pool, it's going to delegate, it's going to call the submit on thread pool, and it's going to be happy and it's going to run free. So, I just delegated my task. Great. But what happens when everything is full? So when thread pool and the queue is full, well, the default is, what's the default? It's just going to grow and grow. We're never going to know. So what happens when the queue is full and the queue is constrained? When we use this constructor that I shown you before. So there are a few policies. One of them is caller runs policy. And it means that, well, I want to submit this task, but there is no space, so you have to run it. The other one, the best one of them, and the default one. So whenever the queue is full, the queue has to be constrained, and then this is the default one. When the queue is full, the queue is constrained in size, and there is no more space, the exception, rejected execution exception, is thrown. So it's fail fast. We already know that something happened, and we can deal with it. Well, the other ones are discard policy, so whenever the queue is full, well, just drop it. And discard oldest is whenever the queue is full, kick out the guy which has been waiting for the longest time. So if your data goes, is not the freshest data is more important, you can just use it. But the most sensible one is abort, meaning I'm just going to throw an exception. Of course, you can write your own implementation of rejection policy. It's easy to do so. And you can, add logging, add counters, add some kind of a metrics, so you know that your queues, that your thread pools are full. Okay, so what about this? We have 80 threads starting, only after the traffic started flowing. Why is it so? Well, thread pools are actually quite lazy in their nature. So whenever you create a thread pool, no threads are started unless they are needed to. So, nothing happens, but then when the task comes and some computation is done and the thread is once again freed, it stays in the thread pool to be reused by later computations. And the amount of time it's going to stay in the thread pool is actually this keep alive time and keep alive time unit you've seen in the constructor before. But the most important thing is that thread pools are lazy, but once the thread has been created, it will be reused. What if we wanted to change this behavior? So what if we actually really want our application to start quickly? And once it starts, to have all the threads in place. Well, there is this method on thread pool executor, pre-start all core threads, and it's going to start all your core threads in the thread pool. So the amount of threads that has been defined in the constructor as core threads. If it's the same amount as the maximum pool size, it's going to be just all threads. So what it does, this method, it's really simple. Just iterates over the threads and submits dummy tasks until all of the threads are created. So that's the graph of what application does. And if you would like to create the similar graph for your own application, well, starting from JDK 9, now Java 11 probably, there is this thing called unified Java logging, and it actually really simplifies creating this kind of log outputs from your system. If you just add this, you're gonna see every time a thread is created or a thread is born with all the identifiers, not the names, but identifiers. It's actually possible to merge it all together. So that's all from me. If there's something you should take away from this, first of all, remember, Java threads are the same as system threads. So, whenever you use the one, you get the other one. And they're quite expensive when you create them, so try to manage them and use thread pools. But don't believe the defaults, check them. For example, with Spring, always use custom thread pool, not the default one. And with executors, at least try to always create an executor with a bounded fixed queue size, because otherwise, memory is only limit and your application might be in trouble. So thank you for your attention, and I will take a look if there are any questions on Slido. Yes, should I? Okay, let me see. Thank you. So there is one question. What is the best way to stop running thread? So this is a very good question, and I'm not just saying so because I should. Because actually there is no way to stop a running thread unless it wants to be stopped. So if you start a thread in Java and you make it so that it does not respect any rules, like it does not listen to interrupts, or it listens to interrupts and just ignores them, like, thread.interrupted or interrupted exception for sleeps, there's no way to control it. So you have to take care to always, whenever you have a thread which might take long to complete, to use things like, while true and thread.interrupted, because only this way, whenever this thread is interrupted, you're gonna know about it. I remember one of my friends told me that he tried to kill the JVM thread from outside the system, from the system, and it crashed the JVM. So, don't do this at home. How to find out the right size for a thread pool? I don't know. Well, okay, so my approach is always you can come up with an initial number, like, if you do some maths and you know that you have 20 concurrent requests per second and each lasts for, half a second, then you should, have this size of a thread pool. But this is like the initial size, and things can change in time. So I'm the strong proponent of adding different kind of metrics into your code. And one of them would be measuring your thread pools, like measuring the utilization and the queue utilization of your thread pool. So whenever things change, well, initially you'll just know if the thread pool is utilized, underutilized or overutilized. And as things change in time, like, the traffic gets bigger, usually once we set something in the properties, we tend to forget about it and just, roll with it for the next 5 years. But if you have metrics, you will be able to spot that the thread pool size that once was good enough, was perfect, is actually getting a bit too small, or is getting a bit too big. So I would say just measure it. Add logging or add metrics, like drop wizard metrics or micrometer metrics in Spring, and use them with thread pools. Okay, can you send an interrupt to a thread from a system command? That's a good question, but I don't have an answer for it. I mean, I never tried this just to target this specific one thread. So actually, I have no idea. Sorry. Okay, so no more questions here. If you'd like to, chat with me, I'm gonna be here. I'm gonna be here for the rest of the day. And enjoy the conference, and thank you once again.